Again, good morning and welcome. Today is Tuesday, March 30th. Next time we're going to meet is going to be on April 1st, which is Thursday. And Thursday we have lab, so it's very important that you guys need to complete the lab. The instructions for the lab should not be hard this time around. And we will go through them. And then also on we have lecture today, so we're going to really do the continue with chapter 26. Last time we had a discussion from chapter 26. Basically what we did was we introduced Kirchhoff's rules, which are critical for solving any kind of circuit, okay? The two rules are, the first one has to do with the junction rule that basically state that the sum of the incoming currents and the outgoing currents is equal to 0. This sum is algebraic sum, basically, in the sense that if I say incoming are positive, then the outgoing are going to be negative. Then in this case, by conservation of charge, that this sum is 0. In the sense that if I say the incoming are equal to outgoing, it's the same thing. So if 10 amperes come into the junction, 10 amperes will live somehow from different branches, not necessarily one branch. So the junction in here assumes at least they have 3 branches connected to the same point. So in this case, there is at least one of them is incoming or 2 of them incoming. And if one of them is incoming, then 2 of them must be outgoing. And if 2 of them are incoming, then 1 of them is outgoing, and so on and so forth. Now, that is basically the idea behind it. It's conservation of charge. Because that's going to give me a condition of the currents. So the junction rule is very important. The other one also is the loop rule. The loop rule starting from any point in here, counting, and this is very critical. We're going to do 2 problems today. Let me grab the book first. We're going to be doing 2 problems today from this chapter, where we're going to go through this rule. The loop rule, starting from any point in the loop, it doesn't matter. I like to start immediately and below the battery. You don't have to. You can start at any point, okay? And then if you come back to the same point, then in this case, and count the drop in potential, which is a key word in here. So that means if you encounter the battery from negative to positive, that is actually a rise in potential. So if I'm counting the drop, so that means actually negative drop because it's a rise. Okay, just follow the current and then it makes sense for you. If you're counting the rise in potential, then in this case, if we go against the current, actually it's a negative rise, which means it's a drop. So that's the only thing that is kind of bothersome a little bit. If you overcome this technical thing, I think you can solve any circuit. I think you can take any circuit and you basically tear it apart, okay, and be able to do it. So there was some pending issues though when we were doing the charging of the capacitor. So let's finish that because there's going to be a lab by itself. So we need to really finish that idea, and then we're going to do problems 19 and 29 from this chapter today. There will be more discussion problems this Thursday, potentially going all the way to Monday Tuesday of next week problems. And then we're going to introduce chapter 27, albeit chapter 27 is not going to be part of this exam, but it is important. Chapter 27 has to do with magnetism, so it's going to be part of the second midterm and the final. So it's still important.
Professor, our first exam is when we come back from spring break, right?
Correct, yes. So
okay.
Immediately after spring break, that week is reserved for exams. So you guys are on Tuesday, Thursday exams, which means that we're going to have those days, basically one day for exam for you guys and another one for another group, but the other group will be doing stuff on that day related to chapter 27, okay?
Okay, so 21 to 27.
The date, I don't remember. I don't know. Probably, yes. Maybe you're right, okay? But it's going to be immediately after spring break. After spring break, all classes, health classes, basically, they will have their exams on campus. I have 2 other classes that I'm going to do their exams on on Canvas.
Okay.
You're with that. Physics 10 and physical science 1, and those I'm going to do them on campus. I mean on Canvas. Sounds correct. Okay. Anyway, so let me put a marker in here because I was doing in here something earlier. So let me go to chapter 26. Okay. So we have a bunch of problems from this chapter that we're going to do. And so let's put the book right now for aside and finish chapter 26 first. Okay. And then we're going to, so let me share the screen. Okay. Another word of caution. Okay, since we talk about exams, so it's worth talking about it too. What do we have for review? Two critical things. The biggest one is the one that we're doing problems in classroom. You need to have them fully understood because you're not going to get them similarly. You're not going to get the same problems, but the ideas are from there. Plus the homework problems. So they must be fully basically done, developed, and everything else. Okay. You have quizzes on almost every chapters, groups of chapters. So you will have those too. Okay. So this is in terms of the review exam. So there will be no day, for example, where we say, okay, today we're going to do an exam review because we've been doing it from day one, basically. That is the exam review. Okay, makes sense?
Yeah, that makes sense. Do you have any like past exams from previous classes that we could use as kind of like an example?
It's not, every time I make up my own exams, basically, number one. Number two is they're going to be different. So it's not going to be very helpful, honestly. And the other thing also that you need to know is, although the exam is going to be on campus, I will have 4 versions of the same exam. Each version is completely different of the other one. So in a sense, because I have another section of Physics 4B, that section of Physics 4B will have 2 complete different versions of the exam, and your class will have 2 different versions of the exam, and 2 students sitting next to one another will have completely different versions of the exam, not numbers, not completely different. So I don't know if it's going to be very helpful to give you that, because it's going to be really, I would say then these problems that we're doing in class are actually a better option than that one. Okay.
Okay. So basically just go back through the lectures and see which discussion problems we did and kind of use that as our exam prep.
That's very good. That's one thing. Okay. Don't forget about the homework also. Okay.
And the homework. Okay, that makes sense. Thank you, Professor.
Okay. So let me share the screen. And are you guys looking at where it says stored energy in the capacitor and all of that, and discharging of the capacitor? Yes, no?
Yes, it's there.
Very good. Because sometimes I share something and I don't share something and I think that I am, and then it goes very long before I realize I was not doing it. Okay. Come on. All right. Why it's not writing? Okay, so today, last time, if you guys remember, we took this situation. Let me go back all the way to the starting point in here. So we took this circuit, and basically what we said there is we had no charge in the capacitor. At t equal to 0, there was no charge in the capacitor. And we wanted to build the charge in the capacitor. We wanted to put a charge in it, okay? And that charge, we called it Q. We didn't know what it was because we brought an EMF, in this case, a battery, basically. And we had it ready before the switch was thrown into the on position. And then we have a resistor R in here. And we wanted to see how long it takes for the charge to charge, for the capacitor to charge, and second, how much charge it will have. So we closed the circuit, knowing that at that time there was no charge in the capacitor. This is the rate at which the charge was building up, piling up in the capacitor. So the current is the rate of charge in this case, how we're going to build this charge. So obviously, if I wait a little longer after t equal to 0, there will be some charge, probably not the full charge, but some charge Q as a function of time. That is going to ultimately grow to become the big Q that we're trying to find, okay? And I, of course, is the rate at which we're going to dump these charges on the capacitor, okay? So this is basically the idea behind it. We use Kepler's rule in here. I mean, Kepler's. Kirchhoff's rule in here, I'm sorry, getting my names completely confused. And we came up with this equation. We solved it and we found actually the rate at which, the charge itself is time dependent. It goes from 0, because if you plug in t equal to 0 here, exponential of 0 is 1, 1 minus 1 is 0, and times c epsilon, that is 0. So initially, yes, t equal to 0, at t equal to 0, q is equal to 0. But as time move on toward infinity, this exponential becomes 0, and it will have 1 times ce. For that, we know then the charges. It's c, the capacitance, times the EMF. Then we found the current also, the rate at which the charge is charging. Those two equations are needed actually for a lot of your homework problems, and sometimes to solve other things. So this equation, this is the current, and the other one is the charge. So this is the charge. This is how we're building this charge. At t equal to 0, the exponential is 1, and the current is actually maxed at epsilon over r. And then at t later on, when time goes by, as time goes by, the current drops exponentially. When t goes to infinity, the current goes to 0. Let's analyze this situation clearly and see what's going on first. Okay, I know the RC is a time characteristic, and I made the big fuss over numbers. Usually tau is very small. Sometimes you really don't want it to be too small. Sometimes you want it to be large, okay? You want to have time to build up this charge. So you are going to basically tinker with this R and C to make this tau whatever you like, okay? So you can make R big, for example, 10,000 ohms. Then in this case, obviously, this number will grow by 10,000 or by 1,000 or something like that. So it's going to be of the order of a second. That's why there is that warning behind the electrical devices and electronics and everything else, that when you unplug a device, please do not put your hand right away in it. Because if you do, there might be charges there that are still in the circuit. So if you put your hand, you're going to close the circuit. And instead of going through that 10,000 K or 10K, or maybe even 100K resistor trying to discharge, get rid of it, it's going to go through you. And it's going to cause damage. So you don't want that, okay? So this is one of the reasons. There is another reason, even inductors, and we're going to introduce that concept later on in chapters 28, I think, or 29. So once they are introduced, then we'll also have another way of storing energy in a circuit via inductors. That's why there is that warning, big warning on the electronics, especially heavy machinery, that can have actually a huge capacitance in there where C is big and R is big. So it still takes a long time for it to get rid of this charge, okay? So in this case, it's actually charging. So the tau in here is a characteristic. If I wait, for example, 1 tau, I have actually 67% of the charge, or about 2/3 of it is actually charged. If I wait 2 tau, I have almost 90% of it charged, more than 90% charged. If I wait 3 tau, it's almost 99.999 something charged. So tau is really gives me a scale of how how long it takes for me to charge the capacitor. So tau is a critical concept. That's why R times C, we always are, if we're engineering this device, we have to really cook this number in such a way that is convenient to us, depending on what we want. This is one point. The second point, immediately after the circuit was closed, this is T, by the way, when the switch was turned on, the current was epsilon over R, as if nothing else is in the circuit, because look at the circuit in here. Immediately, when I close this one, the current entire circuit is epsilon over R. This is immediately after T equal to 0. Obviously, it starts to decay. But in this case, there is an EMF epsilon in here, and there is a resistor, as if there is nothing in here, as if this is a wire only. That's it. So when immediately you turn on the switch, if there is no charge in the capacitor already, treat the capacitor as just a short circuit. So the capacitor is shorted in this case. That's it. So that's the question. When they ask you immediately, when we turn on the switch, find, for example, the current, then you don't need to do all of this calculation. Wherever you see a capacitor, just replace it by a line. That's it, as if it's not there, okay? However, when T went to infinity, When we waited a long, long time, the current became 0. So when t went to infinity, the current dropped to 0. There is no current. If you look at it, it exponentially decayed. It went to 0. So that means after a long, long time, this becomes like an open circuit. This point in here and this point in here, there is nothing between them. So when the charges try to go this way, they cannot because it's fully charged. You cannot, the current is the rate at which you're putting charges, but these are fully charged now, the capacitor. So it's not going to allow any more current to go through it. So after that, it becomes an open circuit. So when they tell you to find something immediately after the switch is thrown on, and there was no charge to begin with, that's a condition actually, then treat the capacitor as if they are just a wire, continuous wire. Ignore them, basically. Just connect a wire, straight wire, like short-circuited wire, basically. Like take a wire around them and that's it. Wrap it around them. They don't matter in this case, basically. If they tell you after a long time, what they are saying in this case, that they are fully charged, and just break them. They open the circuit, basically. There is no current flowing through them. That means I through them is equal to 0. Granted, there might be something else on this side. There might be another resistor, for example, in here. If there is, then there is a current going through the other part. But in here, at least through these 2 points, there will be nothing. Is this point clear? Yes?
Yes, it is.
Very good. This is the item that I want you guys to remember in here, the item of the discussion. Treat the capacitor as short-circuited, or short-circuit the capacitor, short-circuit the capacitor immediately after t equal to 0. Okay, and then treat the capacitor as an open circuit after long time. Okay, so the keyword in here, immediately after. And in here, a long time. When they say a long time, you guys know that probably it's maybe a fraction of a second because of that tau. That's the only thing that is basically characteristic of that. You guys understand? So this is a very important thing on how to solve problems involving capacitors and resistors and how they work together. Okay, this is in DC circuits, by the way, only in DC circuits. In DC circuit. That's the only thing we know so far. Okay, that's basically an EMF that is constant. If the EMF changes with time, then the capacitor is going to change. Then in this case, we cannot have a control over it. Depending on the frequency, then on how the voltage changes, then in this case, you're going to have to fix that. I mean, you cannot do between this and that, this and that. So the capacitor will have a say in this situation. But if it's a current, steady current, it's going to kill it after a long time. So the question that we asked last time is the energy issue, and we need to answer that question. If I wait a long time, the charge that is going to be stored is C epsilon, and then if I divide that by 2C, the C squared cancels the C, and I will be left with the C and divided by 2. So this is how much energy is stored in the capacitor. And I asked last time, and I think you guys answered it, where did this energy come from? It came from, because at the end, the capacitor is fully charged, it has energy, Q squared over 2C. So where this energy could have come from in this circuit again?
The battery itself.
That's the only source of energy in the circuit. Thank you very much. So that's the only source. So let's see how much energy was delivered by the battery. Obviously, it has to be at least this number, at least 1/2 of C epsilon squared. If it's more, then I need to know where the other missing energy went. So that is the question. Okay, so we found that the energy in general is given by the charge times the voltage, okay? The voltage in this case in the battery is just the EMF, so it's dE dQ. So this is for the battery. So this is the rate at which we're really this is the energy we take at every time we take an amount dQ from it, okay? We have to fight that the EMF of the battery, and that's basically how this expression is. So if I want to find the power, which is du over dt, this is the rate at which energy is drained from the battery, because at the end of the day, that's what you buy when you go to the store and pay for a battery. You're paying the energy in it, and each time you connect it, you're taking some of that energy. This is the rate at which you're doing that, which is just going to be the EMF times dQ over dt. And what is dQ over dt again? Isn't that just the current? Yes? Isn't just this guy in here? dQ over dt? Make sense?
Yes, it does.
So now we have to find the energy that was taken from the battery. So this is the energy from the battery. I'm gonna write it E bat, okay, U bat. So in this case, it's the integral from 0 to infinity. Remember, it took an infinite amount of time to charge the capacitor. So we're going to integrate from 0 to infinity this power, which is time dependent because this current is time dependent, times dt. So we start from 0 when we turn the switch, and we're going to wait an infinite amount of time for it to charge. Obviously, if I do this calculation, it's epsilon times the current. The current is epsilon over R times the exponential. So it's the integral from 0 to infinity of this current, which is epsilon over R times the exponential of negative t over RC, and this is dt. Okay, if I'm going to do this integral, I'm going to take epsilon over R as a common factor, which is epsilon squared over R then. And the integral of the exponential is just an exponential, with the exception that there is a coefficient in here, which is negative, sorry, the inverse of that number, which is negative RC times the exponential of negative t over RC, evaluated between 0 and infinity. At infinity, exponential of negative infinity is 0. At 1, I mean, at 0, it's 1. So this value is actually equal to 0 minus 1. And 0 minus 1 times the negative 1, that's going to be a positive number. The R and the R cancel, so I will have C epsilon squared. So this is how much energy is taken from the battery. Half of that is stored in the capacitor. 1/2 of C epsilon squared is stored in the capacitor. So here is the story now where we are in terms of the energy inventory. So when we took an inventory of the energy from the battery, we took C epsilon squared. That on the capacitor we stored. So this is stored. This is taken or drained. So we drained and then we stored 1/2 of C epsilon squared. Do we have a missing amount of energy in here or not? And how much? So we took C epsilon squared, we stored in the capacitor 1/2 of C epsilon squared. So do we have a missing?
Yes. Would it be in the form of heat which is lost?
Yeah, 50% is here. So there is a 50% that is missing. Do you guys agree with Byron that that's probably where it went? It went to the resistor?
Yeah, I can see why. I was kind of confused, but I think I understand.
Okay, very good. So because now half of it, 50% is stored in the capacitor. So what Byron is suggesting is look at this resistor in here, and maybe it's heat, and that is the heat that was gone in there. So we need to account for that, okay? So let's see how much energy is dissipated in the capacitor, in the resistor, I'm sorry, because capacitors store energy. That's actually why it's good. So heat dissipation or energy dissipated, wasted if you wish. That's another thing. In the resistor, of course. So that is going to be, again, it's the same expression, except that the EMF now across the resistor is just Ri. So I have an Ri times I, so it's going to be Ri squared. So the power then in the resistor is going to be just the current I times the voltage, and the voltage is given by Ohm's law. So this is going to be Ri squared. So then the energy in this case in the resistor, use of R, is going to be the integral again from 0 to infinity, because as long as we were charging, which took an infinite amount of time, we were actually wasting energy in the resistor. So this is the expression that I'm going to integrate. Epsilon, I mean the I, the current has this epsilon over R times this exponential. I'm going to square this quantity. So I'll have an epsilon squared over R squared times the square of the exponential, which is just the exponential of 2 times. So it's going to give me epsilon squared over R squared times the exponential of minus 2t over RC dt, okay? Again, R squared and R cancel, and I'm left with one of them. And this value in the resistor, use of R, is going to be epsilon squared over R times the integral from 0 to infinity of the exponential of negative 2t over RC dt. This integral of the exponential, we just did it, except that the exponent has changed, that's all. So it's going to be the inverse of this number, which is RC over 2. And the boundaries of integration are the same as before. So the answer is epsilon squared over R times negative RC over 2 times the exponential of negative 2t over RC evaluated between 0 and infinity. Now, this quantity is actually at infinity is 0, at 0 is 1. So this is actually still negative 1. Negative 1 times the negative, that's positive, and the answer, of course, the R cancels the R. And it would be left with a positive C epsilon squared over 2. So that is where the other 50% is gone. So another half of C epsilon squared went to the resistor. So this is wasted in the resistor in the form of heat. Makes sense now. So we have fully accounted for the energy. So while we were charging the capacitor and storing energy in it, some of it or half of it went to be stored, and the other half went to be wasted in the resistor. So this is how the circuit looked like still. And so this is basically was this full story for it. Do we have it all covered now? Yes. Good. A lot of these things are new to you guys, so it may be hard to basically, but the more you do it, the easier it gets. Good?
Yeah, good.
Okay, very good. So we're gonna tackle the other issue around backward, basically. So now what we have in here in this circuit, I'm gonna bring a capacitor that has actually already a charge in it. I'm sorry, let me write it Q naught. So initially it has a Q naught in it. Okay. I'm gonna put a switch now. And when I take the switch into position now, at t equal to 0, Q is equal to Q naught. Okay. And this is R. I expect I that is equal to 0 because this was open, so there was no current in it. Later on in time, the charge dropped from Q naught down to Q. And this will become negative Q. So this is later in time. and the current will be flowing in this direction, I sub t, okay? The only thing about this circuit now is I of t is not charging the capacitor, but rather it's discharging the capacitor. So the rate of discharge, I sub t, is expected to be negative dq over dt because q is going down. So the current is pushing now the charges, because once you close the switch, then in this case, charges positive will move to the negative and they cancel each other. Once we run out of energy, we run out of energy at that point, because there is an energy right now at t equal to 0, and that energy in the capacitor is equal to 1/2 of q squared naught over c. So that's how much energy we have in the capacitor to begin with. So if we run out of charge, we run out of energy in the capacitor, okay? Because of that dependency of the energy on the charge, okay? So this is the key thing in here. It's this relationship in here. This is the rate of change of the discharge, not charge. We're doing it backward now. I'm going to take a clockwise loop, and I'm going to take a starting point. Now I don't have an EMF anymore, so I need to start somewhere. So I'm going to start in here, okay? And come back to it clockwise. So this is my starting point, and this is my finishing point, okay? S usually is the switch. So this is a start, and this is a finish also, the same thing, okay? So when I start from that, the first device I will encounter while this is being discharged is the capacitor, but I'm going in the wrong direction. I'm going from the negative to the positive. So I'm actually rising in potential. When I rise in potential, I write it as a drop with a negative sign. So the first thing I have in here, it's negative Q over C, because that's the voltage across the capacitor while I have a charge Q. Okay. If I went this way, if I went from positive to the negative, then it's a drop in potential, and I write it Q, a positive Q over C. What I'm counting in here, I'm counting always drop in V in this relationship. Okay. Since I am going in the same direction as the current, therefore I'm dropping on the resistor. So this is a natural Ri. So there is a drop in here in this direction with an Ri. In here, actually, there is a rise by Q over epsilon, Q over C. But I'm going to write it in this direction and change its sign, that's all. So it's still the same correct direction, okay? So if I do it this way, then this expression becomes as a drop in V plus Ri is equal to 0, because there is nothing after that. Even the switch is closed, so I'm going back to the starting point. So this is Kirchhoff's rule. Makes sense? Does this make sense?
Yes.
Very good. So I'm going to sub the value of the current from this expression, and I will have an equation for Q, basically, minus Q over C minus R dq over dt is equal to 0. Move this to the other side. So it's going to be dq over dt and divide by R in the same time, equals to minus Q over RC. Multiply by dq, which doesn't make sense, and divide by q, which means that this deltas need to really be deltas, not dt's, not these. So, and then take the limit to do the justify the division. So it's going to be dq over q is equal to minus dt over rc. Now integrate both sides. What's the integral of, again, dx over x? Because that's what this integral
the regular
is.
one, yeah.
I'm sorry? Marcela.
Yeah, the integral is dx over x.
So what is the integral of dx over x?
Like, what is it after we integrate it?
Yeah.
Wouldn't it be x squared over?
No, this is 1 over x. Anybody else, please?
Oh, 1 over x.
It's
So
ln of
That's what Byron is saying. Does this make sense? It's a natural log, no?
Yes.
Okay. And this is just the integral of x, which is just going to be x in this case, except we're doing it on t. Plus a constant. We always have a constant in here, okay? Now, when I take the exponential of both sides, this is going to be Q as a function of time. What I really want, this becomes the exponential of minus T over RC times the exponential of a constant, which is another constant. So I'm going to write it in here as another constant, not necessarily this constant, it's exponential of whatever that constant is. The exponential of 12 is just some number, okay? So just put it in there as another constant. So we know at T equal to 0, Q sub 0 was the initial charge. So this is equal to a constant from this expression times the exponential of 0, and that is 1. So the constant is equal to Q naught. So this expression, Q sub T, then becomes Q naught exponential of minus T over RC. So we have found the rate at which this is discharging, and it's discharging at the same characteristic, time characteristic tau, which is critical, okay, which is very important. And at T equal to 0, indeed, this is Q naught. And then if you wait a long time, it's going to be a 0 because the exponential of infinity is 0. Now let's take the derivative to find the current, and the current better be positive because we took it positive in that direction, okay? Direction of drop. Otherwise, we're building a charge and discharging doesn't make sense. So if it turns out I was negative, then we have a disaster because somebody's pushing current in here, trying to put more charge, and there is nobody in here who can do that other than a battery, and there is none. So right now, if I do the charge, the current I sub t, which is going to be equal to minus dq over dt, and if I take the derivative, it's just now taking the derivative as is, which is just taking the exponent, which is minus 1 over RC times minus, so it's going to be positive Q naught over RC times the exponential of negative T over RC, okay? So this is actually what the current is. So it's a positive value, exactly how we wanted it to be, okay? So if I plot this two, both of them are exponentials and both of them are decaying. They come from some finite value to 0. So I'm going to plot both of them. This is Q as a function of time and I as a function of time. So the charge comes from Q naught and then drops. The current comes from a value I naught, which is Q naught over RC, and drops down in the same exponential fashion, okay? Both of them are exponential decays. The point in here is the time characteristic is the same. One point in here that I need to make an argument for is R times C is in units of time. For example, V equals to Ri. So that gives me the unit. I know the unit for an R is an ohm, but in terms of the current and the voltage, R has the same units as a voltage divided by an ampere, which is an ohm, okay? Also, I know also that V for the capacitance is Q over C. That means the units for C from this expression are the same units as the units of a charge divided by the units for the voltage, which is V. So in this expression, Q is an ampere times second. That is what the coulomb is. This is a coulomb, which is an ampere times second divided by voltage. So if I want to find R times C, which is this product in here, R times C, this is the same thing as volt over an ampere times an ampere times second divided by volt, cancel the ampere. At the end is just a second, okay? So that is basically how we can see this expression. Actually, it's a time. So when we were saying tau is a time characteristic, it really is a time in seconds. So the answer is going to be in seconds. So tau being RC in everywhere in here, it's in seconds. The only last thing in here I'm going to do quickly is the energy. We initially started with Q naught squared over 2C. So where did that go? It must have gone in the resistor to heat the resistor. So if we do the calculation for the resistor, we should find that same number, 1/2 of Q naught squared over C. So let's test that. So the energy in this case, the dissipated in the resistor while we're discharging is going to be R times the integral of E squared. And E squared has this number in it, Q naught squared over RC squared, R squared T squared times the exponential of -2. So it's going to be, again, the integral from 0 to infinity of Q naught squared divided by R squared C squared times the exponential of -2T over RC dt. And again, the R squared and the R cancel, and we'll be left with Q naught squared over RC squared. And the integral of the exponential will bring down minus RC over 2 times the exponential of minus 2 over RC, which we did it several times today, between 0 and infinity. And R and C cancel from this side, and we'll be left with a C on the other side. And in here, this value is actually 0 minus 1, which is minus minus, so it's going to be a positive, and it's going to be a positive Q naught squared over 2C, because there is a C left after we cancel that one. So this is indeed what happened to the energy in the case of the discharge. You had a Q naught over C squared to begin with, but when you discharge it, it's gone actually in the form of heat in the resistor. So that is basically the full story of the energy in this situation. So let's do a couple of problems in here. The problems which we're going to do are going to be mainly circuits in here. So I need to really open a new tab in here. And we're going to call this one. There will be a lot of problems from this one in here, from this chapter. Okay, chapter 26, problems. Okay, so where is my book? Hopefully you guys have already problems 19 and 26 ready, and you already have a piece of paper ready, handy, and you have your pen ready, and you're actually starting to think about these problems, and we're going to do these two problems. So the first problem I'm going to look at is problem. We'll be doing quite a few problems from this chapter, so don't. So problem 19. Did any one of you guys take physics 4C or planning to take physics 4C or took chemistry already?
I am, but I'm taking physics 4C next semester.
Okay. How about you, Bio?
I took 4C last semester.
Very good. How about the others? No? Okay. There is a
Well,
chapter.
I have to pass this one first.
No, it's not a prerequisite for it. Prerequisite is for A.
I know, but for my major, you have to complete the whole sequence.
Oh, okay. Okay. So no problem. Including 4D?
No, because I completed the calculus calculus sequence. So it's just calculus, and then you finish the physics sequence from A to C.
Okay, no problem. Anyway, so physics 4C has a chapter in it, chapter 17. And this is why actually, because I'm teaching also physics 4C, and some of you guys are actually sitting in that class too. And we did chapter 17, and problem 2619 has to do with that, okay? It's really not a lot of things from that one. So the problems that I'm looking at right now is problem 19. And today we're going to do problem 19 and problem 29 from this chapter, okay? So as I said, hopefully you guys have this thing going. So problem 19, it says in the circuit shown, and it gives you a very, very ugly looking circuit, or it looks like ugly. So we're going to make sense out of it. A 20 ohm resistor is inside 100 grams of pure water. So you have pure water, not alkaline, not with salinity. Okay, not alkaline, not with, I'm sorry, no salt in it. What am I saying in here? Okay, that is surrounded by insulating styrofoam. So that means the current does not leak outside. If the water is initially at 10 degrees Celsius, how long will it take for it to for its temperature to rise to 58 degrees? So let's draw the circuit first, okay? We have a junction in here. We're gonna fix what's before it. We have a resistor in here, in this junction, and another resistor in this junction, in series with this one. And on this side, on this branch of the junction, we have another resistor, in series with actually another resistor.
Your screen is not showing.
Thank you. That's really what happened typically. I got to do that. Okay. So here is where we are, okay? So we have a junction, and we have, in one branch, we have two resistors in series. In another branch, we have two resistors in series. And actually, there is a third branch where I have two also resistors in series. And this is basically how this section of the circuit look like. And then this is in series with another resistor sitting in here. And this one, actually, there's a battery in here. This is the positive side of the battery. And finally, we have in here another resistor. We really technically should really have a switch in here. I really don't like it when they don't put the switch in there. Okay? Because we want to find the time. So we really need to know time when we start basically the clock to test this thing. Okay? And here what they said is this is a 20. First of all, let's put the numbers in here. This is a 10 ohm. This is another 10 ohm. This is a 10 ohm. This is a 10 ohm. This is a 5 ohm. And this is a 5 ohm. And this one also is a 5 ohm. And this is a 20 ohm. Okay? And the battery is 30 volts. Okay? So what they say in here is that they put the whole thing in here with they contain it in a box of water, pure water that is. In it, they have 100 grams of water. And they want the temperature to go from 10 degrees Celsius all the way to 58 degrees Celsius, okay? So this is basically the idea behind it. How long does it take? The question is the time t, okay? Here is the deal. There is one thing about water, first of all, and that is where physics 4C comes into handy in here. For water, in order to raise its temperature by an amount delta T, and if you happen to have an amount of mass m of that fluid, of that water, you need to introduce the specific heat of water, and that gives you an amount of energy that is needed to raise it. So this is the amount of heat to raise. I mean, the sequence in here in the book is actually, we're doing chapter 26, and chapter 17 comes way back. So the book has no problem with the way sequence is. It's really the way that we sequence our course is the problem. I mean, in a sense that some of you did not really see chapter 17 before 26. But that's really how this is coming in here, okay? So this is the amount of heat needed to raise the temperature of m grams of mass m by an amount delta T, okay? The amount delta T after this is 48 degrees, because we're going from 10 degrees to 58 degrees. So we need 10 degrees in here, 48 degrees to go from 10 to 58. And C now is the specific heat. This is characteristic of every material. Every material has its own specific heat, okay? Some materials, they're easier to raise their temperature than others. So how can we tell? It's their specific heat that makes a difference. For example, iron has a lower specific heat than water. As a matter of fact, most materials have specific heat less than water, okay? So it takes a a huge amount of heat to raise the same amount of water versus another like iron, for example, okay? So specific heat for water actually is known to be 4,190 joules of energy for just 1 kilogram of water, or 1 liter, that's 1 kilogram basically, to raise its temperature by 1 Kelvin, or 1 degree Celsius. It's the same thing, okay? Because we're looking for temperature difference, so we really don't care if you use Kelvin or degree Celsius. Do not use Fahrenheit though for this number. So I'm gonna use degree Celsius because we have the numbers in here in degree Celsius. So to raise it by 1 degree Celsius, and you have a ton of water, 1 liter of water, which is probably about this much of water, you need this much energy, 4,190 joules, okay? Or 1 calorie. That is the same thing, okay? So that is the formula that we need. Now, I want to go through this one. So I know how much energy is really needed. So I need this much of heat. So I can compute the heat is simply equal to Q. I know the mass is 100 grams. That's what they told us. The amount of water is 100 grams, which is 0.1 kilogram. So it's 0.1 kilogram times the specific heat of water, 4,190 joules per kilogram per degree Celsius. And the difference in temperature is 58 minus 10, which is 48 degrees Celsius. So the degree Celsius and degree Celsius cancel, the kilogram cancel the kilogram. And where is my calculator? Did I close it? It is closed. So that's no good. Mathematics. I need that calculator. So what I have in here, I have 0.1 times 4,190. I know you're saying, why don't you just put 419? Okay, that's fine. I can do that. But I'm going to try to be careful in here, not to make a mistake, okay? And this is what I suggest you do when you're doing problems with exams and things like that. Do not do quick calculations, because that's where a lot of mistakes happen. That's at least with me, okay? So I'm recommending that you actually do the same thing. Do the steps on the calculator as you're doing them in here, and do not basically do too many steps at once. That's what I make a lot of mistakes. So this value of the energy is 20.1 kilojoules. To be more specific, this calculator is giving me 2,112 joules, okay? 20,112 joules. That's a lot of energy to raise its temperature by that much. So here is the thing. If I can find the current that is coming through the circuit, which is the same current going through here, I can find the power in this resistor, which is just Ri squared. We showed this one today, that this is Ri squared. This is the power. Since I know how much energy, the power and the energy are just related to one another as being then in this case, Q is equal to power times time. So the time in this case should be just, because the power is Q over T. So in this case, it's going to give me the time with just the total amount of energy divided by the rate at which we're going to find the dissipating heat. So because the resistor is the one that is raising the heat, this is actually a resistor using to warm your coffee, for example, okay? So that is exactly what you're doing. You're using a resistor in there. So all we need is to find that current. For that, what we're going to do in here, we're going to find the R equivalent. That should tell me how much current is leaving the battery at any given time. So that is the current that is going to heat the water in here. So we're going to get rid of this complicated circuit and come up with an equivalent circuit to it. I have two resistors in series, 10 ohm and a 10 ohm. They resolve to a 20 ohm because they're in series. So you add up just the numbers for series. I have a 10 ohm and a 10 ohm for this branch, which they just add up also to a 20 ohm resistor. I have a 5 ohm and a 5 ohm in this branch, which they simply add up to just 10 ohm, 10 ohm, okay? Now in this circuit, what I have a 20 and a 20 and a 10, all of them, they're actually in parallel. So the R equivalent in here, and this is where you have to be very, very cautious, because I have seen this time and again where students make mistake on it. So you take the inverse of 20, you add this 20, and you add to it the inverse of this 20, and you add to it the inverse of this 10. And when you do, this is where the step that I have seen it people forget to do, and that is to invert the answer. Because what you have in this case when they are in parallel is the inverse of the equivalent resistance is the sum of the inverses. So if you really want to find the resistance equivalent, you have to invert it itself. So 1 over 20 and 1 over 20 is just 2 over 20, or 1 over 10 actually, and 1 over 10. 1 over 10 and plus 1 over 10 is just 2 over 10, or 1 over 5. And when I invert it, it's going to be a 5. So this whole thing is just like a 5 ohm. This whole circuitry in here that looks ugly is just like one resistor of 5 ohm. We could have gotten rid of this 5 ohm and this 10 ohm and this 10 ohm and this 10 ohm and this 10 ohm and just basically worked with that 5 ohm by itself in there. It's the same thing. Okay, one of them is fine. If this is the purpose of this thing in here, if that's what we really want to do, okay? So we have now 5 ohm in series with the other 5 ohm, and in series also with the 20 ohm, because the same current is coming through the 20 ohm, go through this complicated geometry, which is just like equivalent 5 ohm. So it's actually a 5 ohm now going through this, the 5 ohm. So it's the same current going through the 5 ohm, which is the same current coming in here through the 5 ohm. So all of these resistors are just one resistor of 5 plus 5 plus 20, and that is 30. So the R equivalent overall, this is how the circuit really look like. It looks like this. Where this is the R equivalent for the entire circuit, which is 20 plus 5 plus 5, and that is 30 ohms. Obviously, if I do the loop rule, it doesn't matter which one in here, the voltage drop in here between this point and this point, it's the same voltage drop between this point and that is 30 volt because the battery is 30 volt. And the current then is going to satisfy 30 volt must be equal to 30 ohm times I. And I in this case then is becomes 30 volt over 30 ohm, and this is 1 amp. So the current that is coming from the battery is 1 ampere going through the 20 ohms, 1 ampere, splitting itself in here between these 3 branches. I don't know how much. We can find it if we really are interested. Okay, on this branch, it's basically 5 times this current plus 10 times this current plus 20 times the other current plus 20 times the other current must be equal to this same thing in here, which is the current that is split in here. So basically, if you are interested, and this is not the question, it has nothing to do with this question here. So this current of 1 amp splits itself between I1 and I2 and I3. How much each and every one of them? They are in such a way that 1 amp is equal to I1 plus I2 plus I3. But I know the voltages are the same between this point and this point because they are in parallel. So I know 20 ohms times I1, 20 times I1, is the same thing as 20 times I2, is the same thing as 10 times I3. So I could get rid of one of these I's. I could get rid of I2 and I1 and use just in terms of I3. So, or do it the other way around, I'm sorry. I3, then it's clearly I3 is equal to 2 times I1, which is the same thing as I2, or 2 times I2. So in this case, this is I1 plus I1, because I2 is the same thing as I1 from this relationship. And this I3 is just twice as much as any of the other two. Let's call it I1. So this I2. So this is, the whole thing is 1 amp. So I have 1 I1 plus 1 I1 plus 2 I1, that's 4 I1. So I1 is actually 0.25 amps. This 2 is 0.25 amps. And this is twice as much as any, which is a half an amp. So if you're really curious trying to find the other currents, you can. That is the whole thing. You can find the current anywhere you want to. This is not part of the question. I know we're going beyond the question, but I'm trying to tell you in here that you can calculate whatever you like at this point. So if the question was, let's say, for example, instead of putting the tank in here, they put it around the 5 amp, then in this 5 ohm, then in this case, you're going to take the 5 ohm times this current squared, which is 0.5 squared, and that is going to be the power, not this power in here. So if they put the tank in here instead in there, you can calculate it in here, whatever you like, okay? So let's get back to the problem. So we have the power now, since we know the current is 1 amp, and the power is going to be 20 times 1 squared. So for this part in here, we know the power for this particular problem, the power P is across the 20 ohms. Let's make it clear, okay? That's what we're calculating. It's 20 ohms times the current squared, and the current squared happened to be 1. So this answer is 20 watt. So the answer in here, the power is 20 watt across this resistor. Whereas if it was this one, it's going to be 5 times 0.5 squared to 0.25, and the answer is going to be 0.75, two and a half watts in here. So it's going to be a lot less power in here if we're going to use this one. So it's not the same, okay? So this is how much power, and we know that the time is going to be the amount of energy, T, is going to be Q over P, and Q is, we found the 20,112 joules divided by 20 watts, and that is going to be, I know the sig figs and all of that stuff I didn't, because in the calculator in here, if I double click on something, it's going to give me the actual value that it has found, which is without the sig figs. So what I'm coming up with is 1,005.6 or 1,006 seconds. How many minutes is that? Divide that by 60 and take the remainder as seconds, okay? So 1,006 divided by 60, the answer is 16 minutes. 60 seconds times 16, subtract that from 1,006. That gives me 46 seconds. So that I know exactly how long it's going to take. It takes 16 minutes, 46 seconds, actually about 46 seconds because of the rounding, to charge, to go from 10 degrees Celsius to 58 degrees Celsius, okay? If the desirable is to boil it, then in this case, we have to go from 0 degrees Celsius to 100 degrees Celsius. So this energy will be more. So the time will be more, okay? Because the numerator will be more, so the time will be more. If they tell you, for example, hey, listen, we want to really bring it to a temperature of 113 degrees or something, then this formula becomes part of the story only. Because this formula assumes that there is no phase transformation, that you still are in the liquid form. Because if you go into a boiling, at some point, the water first has to evaporate. Once it evaporates, becomes vapor, then you're going to increase the temperature of the vapor. So there is some heat that's needed for the phase transformation. So that is something else, okay? But at least if you're sticking in the same phase, this is a correct calculation and there is no problem with it. Does this problem make sense to you guys?
Yes, it does.
It does. I just kind of got lost where you got 46 seconds from, or where you subtracted from.
Okay, that is 1,006 seconds. 1,006 seconds is 16 minutes. And what 16 minutes, when it multiplied by 60, that's going to be 960 seconds. So the difference between 960 seconds and 1,006 is 46 seconds. So basically 1,006 seconds. That's the correct answer. But of course, if you tell somebody, how old are you? They're not going to give you the number in seconds. I'm what, 50 million seconds or something? I have no idea. In seconds. So usually people use the minutes and hours as a unit.
Alrighty. Yeah, okay, now I see it.
And that's basically how it's practical sense, because I know that an hour has 3,600 seconds, okay?
Mm-hmm.
So, and the answer is less than an hour because 1,006 is less than 3,600. So we know that we are somewhere between basically 0 minutes all the way to an hour. So because 1,006 is somewhere in between. It makes more sense to convert it into minutes, that's all.
Oh, okay. Yeah.
So that's all, okay? So because if somebody asks you how old are you or how old the universe, you're not expected to give them the answer in seconds, okay? Then they probably would be very, very angry at you, okay? Like when you go for your driver license or whatever application, they ask you how old are you? In order to annoy them, give them the answer in seconds, okay? Yeah. Okay, so Problem 29. How are we doing in time? We still have good time. Okay, good. So in the circuit shown, they give you a circuit in there. The batteries have negative internal resistance, and the meters are both idealized. With the switch S open, the voltmeter reads 15 volt. Find the EMF E or epsilon of the battery. Okay, so let's draw the circuit first of all to see. First of all, we have a resistor in here. So this is problem 29, just to keep track, okay? And hopefully you guys are doing the same math in here with me. Otherwise, this is not going to work. This is 75 ohms. And we have a junction in here. And in this junction, in this branch, we have a 20 ohm resistor. Okay. And then we also have an EMF that is pointing in the up direction. And they tell you we don't know what its value is. We know it's some EMF, but we know it's a battery in there, but we don't know its value. And there is a 30 ohm resistor on this branch. Followed by another junction in here, where we have another battery in here. And this battery, we know it's EMF, it's 25 volts. And there is a switch now, S. And this is basically the other branch of that side in here. And we have an ammeter, followed by another resistor now of 50 ohms. And the whole circuit closes in this point in here. So we have 50 ohms in here. But we also have a voltmeter. Okay. So what they're saying in here is that the EMF, first of all, has no internal batteries. They're all ideal things. And then also the meters, both of them are ideal, meaning that this one has no resistance. This R is equal to 0 for this one. That means the voltage drop between this point and point is 0 because it's an ideal one. And the resistance in here is an open circuit. It's an infinite resistance. That means that the voltage drop between here and here is exactly the voltage drop between this point and point. That means there is no current flowing through it. I is equal to 0 going through here, and B is equal to 0 for the ammeter. That's exactly what this thing is, okay? So when you have an idea, technically, usually they have internal resistances. This one is not really quite infinite. It's very large, but not quite infinite. So there is a little bit of a current going through it. And this one is actually not exactly 0, but it's finite because it's circuits anyway, it's wires, just like these wires that are assumed to have no resistance, but they do. So it's the same situation here. This thing is idealized. So what they said in here is that with the switch open, so we are in this position, we have it open, okay? So that means there is no current flowing in here. So if there is a current coming in here, that current I cannot go through this one because the switch is open. So the entire current is in entirety coming through here and going through this resistor. They cannot go through this branch because this is an ideal voltmeter. So it's coming through the resistor. And as it comes through the resistor, it comes back and it cannot go back through here because, again, it's an open circuit. Now it can come to this point where it encounters a branch that is legitimate branch. So potentially, because this is the only guy that is pushing current, potentially this current, which I'm going to call it I30, which is the same thing as of I50 at this point, is the same current when I add it to this I75, the current that is going through the 75 ohms, it must be the current that is coming from the battery because of the junction rule. I have a junction in here, okay? And find the EMF. If I find the voltage drop between this point, I'm going to call this point A, by the way, and I'm going to call this point B. If I find the voltage drop between A and B, and if I find the current flowing through the 20 ohms, I'm in business. I know the answer to the question, okay? Because then, if I know the whole voltage drop, all I have to do is subtract it from this one, but this one is actually a rise, subtract the negative, which means add to it, then I am in business. Then I have found the answer to the question. So that is really how the plan is. but I don't know what the voltage drop from here because I don't know what this current is here either. Okay, I don't know what I-75 is, but I know what the current going through the 50 ohms because I know this voltage drop in here is 15 volt. That's what they said. Okay, when they closed it, the meter was reading 15 volt, and I know that the 50 ohms in here. So 50 ohms must have a voltage across the 50, which is just the 50 ohms times the current that is flowing through it. And that current is the same current that is flowing the 31 anyway. So I-30 then must be the same current through both of them, because there is no current flowing through this guy, is going to be 15 volt divided by 50. And if I do 15 over 50, multiply this one by 2 and multiply this one by 2, this is 100. 15 times 2, that's 30. 100 divided 30 divided by 100, that's 0.3 amps. So we have a 0.3 amp going through this way. Okay, so we know what the answer is. That's 0.3 amp. So if I know what the 0.3 amp is, I can find the voltage drop now between A and B. Let me tell you how that is between A and B. So the voltage drop between A and B, which is VA minus VB, and it has to be VA minus BV. This point A must be at a higher potential than B because of the fact that the current is flowing this way. So on one side, it's 30 ohms times that current. There is nothing in here. So the same 30 ohms, 0.3 amp is going through the 50 ohms. So this voltage drop then is equal to the 30 ohms times the 0.3 plus the 50 ohms times 0.3. And this is 0.9. And this is 50 times 0.3? 5 times 3. 15, 150, 15. So this is 9 plus 15, and the answer is 24 volts. So the answer, the voltage drop between this point and this point is exactly 24 volts between A and B. If I know what this current is, I'm in business, but I don't know what that current is. So let's find that current. Before, part of it is going in here. The other part is going in there. So if I find the other part, now add the two, and now I have the total current that is coming from the battery. So I need this current, I-75. This same voltage drop between on this side, because this current I took at I-75 going this one is actually the same voltage drop going this way. Because I can go from A to B through this loop, through this branch, or I can go through this branch, that's the same thing, or I can come straight through, it's the same thing. So right now I'm going to choose the other way around. Since I know what A and B is, it's 24 volts, it must be 75 ohms times this current. So the 24 volt, which is the VAB, which we just found it to be 24 volt, must be 75 times the I-75. From here, the current going through the 75 ohms is simply equal to 24 divided by 75. And that is equal to 24 over 75. That is 0.32 amps. Okay, so we know the current now that is going on one side, which is 0.32 amps. And we know the current that is leaving, both of them are outgoing currents. They must be equal to the incoming current I, their sum, that is. That is the first law of Kirchhoff. So I then must be equal to 0.3 plus 0.232, which is 0.62 amps. So that's how much current is coming through to this junction at point B. If you're wondering what happened on the other junction, it's the opposite. You have 0.3 coming from one side, and you have 0.32 coming from the other side. And when they meet in here, they add up to give you again 0.62. So the 0.62 amps is the same thing, which is this current. So now I'm going to compute the same voltage drop between A and B using the last basically a branch. So what I say in this case is VAB. I'm going to call this point in between them some point. I'm going to call it point C, for example. Okay. So I'm going to call VAB, which is 24 volts still. We just found it earlier. Must be equal to VA minus VC plus VC minus VB, because that's exactly what VA minus VB is. Well, VA minus VC, that's across this 20 ohms. And we are actually coming this way from VA down to VC. So we're actually going against the current. Sorry. Yeah. Wait a minute. How am I calculating this one? I'm calculating the voltage drop between A and B. So if I'm coming against the current in this direction, so this is going to be a rise potential actually. I'm going to go from this potential to this potential, but I'm going against the current. Since I'm going against the current, the voltage drop against the current is going to be just minus 20 times the current, which is 0.62 amps. And this value is because I'm coming now from the positive to the negative. That is actually an actual drop in potential because I'm coming from positive to negative. Had I come from the other side, then it's a different story. Okay. So in this case, from positive to negative, it's going to be the EMF plus EMF. Okay. So this whole thing must be equal to 24 volt. So if I do the calculation, 20 times 0.62, that's 12.4. So this number is 12.4 with the negative sign. And when I move it to the other side, it's going to be 36. So the epsilon is going to be 36.4 volt. So that's how much EMF is in here. Okay. If you're calculating VB minus VA, if you're doing it in the opposite direction, VB is at a lower potential than VA. So the whole answer is going to be negative 24. Then you're going to go and rise in potential here. You're going to go from negative to positive. So you're counting the drop in potential. So it's going to be a minus epsilon. And in this case, it's going to be plus 24. So if we do it the other way around, let me tell you what I'm talking about in here. If you do VBA instead of VAB, if you do VBA, it's VB minus VA, which is VB minus VC plus VC minus VA. Well, in this case, it's actually negative 24 volts. This is actually, you're going to rise in potential by an amount which is epsilon. So you're going to drop by negative epsilon. And this one, you're just following the current. So it's RI. So it's going to be R, which is 20 ohms, times 0.62 amps. Obviously, this expression will give you the same answer because if you move this to the other side and move this to the other side, the epsilon will still be 36.4 volts. So whichever way you do it, as long as you're keeping tab of the drop in potential, you're in good shape. Because the reason why I did the negative sign to begin with in here, because I came in the wrong direction in the current, going from A to C. If I do that, the current is going up and I'm coming against it. So this drop in potential now is actually a rise in potential because the calculation from this point to this point is the actual drop of RI. If I'm going from here to here, it's actually a drop by negative RI. And if I do that, that gives me the value for epsilon, which is 13.6 volt. Now the 13.6 volt now counts for everything. 36.4 volts account for everything. 36.4 minus this 12.4 give me the exact 24 volt between points A and B, whichever way I look at it. Okay. I really want you to analyze these last 2 points that I'm making in here because sometimes this can be confusing a little bit, but it is key for the rest of the problems. Hopefully, the more problems we do like this, the easier it gets. There is an alternative version for all of these problems when there is a single battery, where you just treat the difference in potential being epsilon and equate everything else to this epsilon. That's fine. But it gets confusing when you have two batteries. Then which battery you're going to use? Obviously, the 36.4 battery will be pushing more current than the 24 volt battery. But then it's not obvious most of the time that it's going to overcome it, because if you have more stuff that is draining power from it, then the 25 volt battery may be more advantageous. So it's better to stick to this convention, honestly. It's going to save the day all the time. Okay. So we still have about 4 minutes. So let's get the last question, and hopefully you guys can come to this one. And if you have any questions, please do not hesitate to ask, and we can come back to this point next Thursday if you like. So let me do the last part of this problem, which is what will the ammeter read when the switch is closed? By the way, the ammeter now is reading 0.3 amp. in this situation. That's what the current is throughout this entire branch. So now when the switch is closed, once it's closed, now we have an, I'm going to call this point in here, point D, for example. D, there is nothing in here from D to this, the same point B, by the way, this is B, this is B, this is B everywhere, because it's the same branch in here, same connection in here. So in this case, once it's closed this way, the voltage drop between D and B is 25 volts. It's the battery, this battery. And that is equal to R times this current, current that is flowing through it. So there might be a different current in here, okay? So it's not going to be the same. So it's not I-30 anymore, it's an I-50 now. So there is a current flowing through this one, which is I-50, and that is the one I want to find. So they are not going to be equal anymore. The current will change because the voltage now has changed. Because this voltage drop will matter now. It's not the same as that one. So there is a situation in here that you need to fix. So obviously I have 25 volt, the voltage drop between the point D that I introduced and the point B that was in there before is going to be 25 volt, first of all, because of this battery, which is equal to the resistor, which is 50 ohms, times the current, and the current is the one that is going to be read by the ammeter. So the current now is going to be 25 over 50, and that is going to be equal to what? Half an amp. So when you close the circuit now, there is a difference of potential that is different from the one it was before. Initially, it was 24 volt going from A all the way to B. Part of that current is going through this resistor and the other part through this resistor, so they were in series. That's what accounted for the current to be 0.3 amp. But now the 25 volt, which is more voltage, first of all, between D and B, is only going through the 50 ohms. If you're curious trying to find the rest of the circuit, you can. Because this battery is trying to push a current now. Half a volt is going through this, half an amp is this way. And this battery is still pushing current in here. So there might be a current flowing in the opposite direction in here. Okay, there might be a current going in the opposite direction in this section. Okay, and or in this section, but it's going to be different than this one. So the currents change now. So this is the reading of the ammeter in the second time. So the first time was reading 0.3 because this one is open. Now once you close it, the voltage drop between this resistor is actually the 25 volt. And because all of the 25 volts is going through it only, the current went up. Not just by going from 24 to 25, but far more drastically than that because of the fact that all the voltage drop is across it, and that's what accounted for that increase, drastic increase in the current. Okay, we're just in time for this to, so I'm hoping that you guys will go through these problems again, and that you did already during this lecture when I was doing it, and then you go through them, and we're going to do more problems. But you need to understand every single step of them. You really need to be master of these things. Good. I'm going to stop the recording. Somebody was going to say something?
I was just going to say, yeah, good. All good here.
Okay, very good. So I'm going to see you guys on Thursday, okay?
Sounds
Thank
good.
you so much, Professor.
No problem. Thank you. Bye.